All right, how's everything today? Questions up to here? Yeah.
Number 8 on the homework.
Okay.
Kind of confused on what it was asking.
What does it say?
It's something about. He has it, 1 second.
Okay.
It was proved that P of n is a tautology over n,
P of n.
which was P of n was 8 to the n minus 3, so that n is a multiple of 5.
Ah, cool. So let P of n be the proposition. 8 to the n minus 3 to the n is a multiple of 5. Prove P of n for all n bigger than or equal to. Let's just go bigger than or equal to 1. Using mathematical induction, because that's the section we're in, right? So base case, not too bad. P of 1 says 8 to the 1 minus 3 to the 1 is a multiple of 5. While 8 to the 1 minus 3 to the 1 is 5, that's a multiple of 5, so that's true. So we got a base case. So to prove P of n for all n bigger than or equal to 1, we need to prove the following. Prove that if P of n is true, P of n plus 1 is true, where n is bigger than or equal to 1. Okay, so we start the same way we always do. P of n, that's a hypothesis. Write out what P of n says. And I'm going to write this as follows. I'm going to say 8 to the n minus 3 to the n is equal to 5 times some number where that number is an integer. That's what it means to be a multiple of 5. It means you're 5 times an integer. Okay, and over here in my ignore section, what am I trying to do? I'm trying to show that 8 to the n plus 1 minus 3 to the n plus 1 equals 5 times some integer. Okay, this one's different from a lot of the other ones we've been doing. A lot of the ones we've been doing have dealt with sums. Show that this plus this equals that. And so to move from the case of n to n plus 1, we add one more thing to that sum. But here we're trying to change this n into an n plus 1. And so my suggestion here is right, we want to show that's equal to 5 times an integer. The only thing we know is that this is equal to 5 times an integer. Can we somehow rewrite this to look at least partially like that? Is there some way to get back to an 8 to the n or a 3 to the n? Yeah, so we can use a little trick here. 8 to the n plus 1 is 8 times 8 to the n. 3 to the n plus 1 is 3 times 3 to the n. So this is absolutely true. This is just algebra, exponents, right? And now we want to somehow change that into something else. So my suggestion at this point is think about it in this form and see if you can do something with that. We can't just, put a k or 5k in here, right? We got to somehow pull out an 8 to the n minus 3 to the n. But if there's some way to factor that out, right, that would give us a 5 times k. And if the thing that's left over is a multiple of 5, then we'd be done. So play around with the algebra. This is purely just puzzle solving, right? It's a little puzzle game. Nothing directly to do with mathematical induction per se, right? Induction is all of this stuff. And then once we know n plus P of n plus 1, then saying, P of n for all n by mathematical induction. So this is something kind of on its own. It's a sub-problem. But I would say play around with that a little bit and see if it gets you somewhere. This typically would not be one of the questions I would grade because it is very subtle. But it's a good one to mess with. And we're gonna spend all of today pretty much working out induction problems on the board, so we're gonna get a lot of practice today. All right, other questions?
So the midterm, is it
Mhm.
gonna have basically everything from homework 1 through 4, or?
So I posted a study guide a while ago. I think I posted it before class started in the beginning of the quarter, but I just noticed it.
Possible midterm? Oh, no.
Yeah. All right, possible midterm topics, basically logic and proofs. So logic is propositions, what's a proposition, deriving new propositions from old propositions, so operations, conjunction, disjunction, negation, ands and ors, and nots, right? Implication, so if P then Q, or the double arrow P if and only if Q, or if you like, if P then Q and if Q then P. Truth tables, converse, inverse, and contrapositive of an implication. So if P then Q is an implication, the converse is if Q then P, the inverse is if not P then if not Q, right? So all of those. Contrapositive is logically equivalent to the original, the others are not. Propositional equivalence, saying that two propositions are the same, and the fact that you can prove those using a truth table, or using various identities like commutivity. Did quantifiers, so there exists and for all, an existential and universal quantifier. And then rules of inference, that purple sheet, bring your purple sheet with you. With all the rules of inference, direct reasoning, indirect reasoning, disjunctive simplification, yeah.
Does the purple sheet count as?
No, that's bonus sheets, so you still get your full 4 double-sided pages in addition to that. Proving an argument is valid, right? So things like this, given P1, P2, and P3, prove Q. Okay, so you've done homeworks on those. So these proofs, right? And then fallacies, fallacy of affirming the conclusion or denying the hypothesis. So make sure you're familiar with those. And they're sort of the incorrect versions of direct and indirect reasoning. And then proofs, we looked at direct and indirect proofs. Indirect proof is a proof by contradiction. We did some theorems about even and odd numbers. Those are good examples of proofs and using proof techniques. And then most recently we've been talking about mathematical induction. There's one question on the exam about mathematical induction. It's only worth 10 points. Okay, most of the questions are 20. So there's an induction question on there, but it's not like, you know, a huge part of the test because that's still a relatively new area and we haven't collected homeworks on that yet. But we're going to spend most of today working on induction. So, yeah.
Would you be okay with us bringing in some old homework assignments that was pages and notes?
As long as it, yeah, within your page and notes budget, sure. That's totally fine. Or you can Xerox the whole book on a little, you know, get a big magnifying glass. That's cool.
I like the little smiley face.
Yeah, induction's always happy. All right, other questions? So there's been a section up here, some practice problems for mathematical induction. Anybody looked at these? I just looked at them for the first time last night. But there's some decent questions here. Prove that the sum of powers of 2, oh, that's a weird one, okay. We did 5, right? And we did 6. Let's break into groups and let's work out some induction problems. And let's just go ahead and start with number 1. So you're doing a weighted sum of powers of 2, 1 times 2 to the 0, 2 times 2 to the 1, 3 times 2 to the 2, and so on. And you want to show that that equals n minus 1 times 2 to the n plus 1. And so for the first one, I definitely want you to be very formal about it. I want you to write down, let P of n be the proposition and say what the proposition is, right? And pick your base case, n equals 1, show that P of 1 is true, and then do a formal proof that P of n implies P of n plus 1. And I want to watch what you do here because I want to make sure that you've got the formalisms down. Getting from n to n plus 1, I don't remember how tricky this is, but let's try it. Just work slowly and carefully, right, with the algebra, because there's a lot of stuff going on. So find some groups to break up into, and let's play with this. Yeah, start with number 1. The algebra is not too horrible on the first one if you work carefully.
N minus 1.
The n minus 1.
N minus 1. It's actually, it's n minus 1 times 2. Yep. And then plus 1
Plus 1.
for n greater than or equal to 1. Oh, it skips, right, skips. Yeah.
He wasn't right. Sorry. You were right. You were right. Oh, okay.
Oh, yeah.
Equals.
I remove
Oh, I did it wrong
first
first time. Okay. So that was n times 2 minus 1 equals 1 times.
For all n greater than, yeah.
So P of n is and you grid 1 equally.
Yeah.
So then we can say, let P be the prop that. Right. Yeah. Say, let P of n we can do the base case.
Yeah.
So this is P of 1. Which would equal, so n would be, yeah, so if n is 1, then 0.
Our base case is
So
I guess we're basically one.
That's just. Yep. N minus one, only one, so this is just gonna be 0 and plus 1 here. Oh, plus one. Yeah, plus 1.
Not worse.
Okay, in this case, and now we need to. Yeah. Well, I guess I'm right. So we'll take P of N, Q to the N as an hypothesis. Yeah. You could write the definition. Yeah, we should.
I'm just gonna try to do more.
You're gonna try what?
I'm gonna try to do
Oh,
more.
nice, yeah.
Let P of N equal this, equal that. So like you said, P of N equals the equation. Oh yeah, so P of N equals the statement. Let P of N be the statement, that's equal to that, and would be the proposition.
Okay, so event is true. Event is true.
Yeah.
So I
You
believe,
kind of figure out.
yeah, that's what we're trying to prove. So if I believe we now plug n plus 1 into here and then add it to both sides. Yeah. From here, from this point. I just did it.
It's, we just want to add one more term.
Yeah, just, yeah.
Add one more term.
Yeah.
So just take this and then we'll just add plus n plus 1 times 2 to the n. And we'll add it to both sides.
Yeah, yeah, right. Yeah, yeah, that's right.
So n minus 1 to the n plus 1.
Yeah, maybe we write out and sacrifice we might do this.
All right, and then here, we have to simplify this.
That would be 1 times 2. I still might have to do this.
Yeah, you can figure it out.
So we
I think
assume,
I figured it out too, actually.
and then we could add
Yeah.
1 to like right there, right?
Yeah.
So are you writing P of N or P of N plus 1, or are you writing something different?
Well, I figured we'd start with P of N, like we assume this is true.
Yeah, that works.
Okay, so I would get rid of where you say P of N plus 1 implies.
Right. So this is P
Wait,
of
2n, I don't, yeah, that works.
So when we added this, we get this finally.
Yes, so we did the simplification. Yeah,
Part of
we got that.
Right.
So yeah, it checks out.
Actually, not seeing where it checks out. I'm going to see the algebra, it's fine, but.
So do we add 1? Or add 1 to this?
Yeah.
Right, we just needed to get that, and we got it.
So this is where I would write a section and label it ignore. And do some scratch work. Right
Yeah,
out
I get it.
explicitly what P of N plus
So then
1
we'd say,
says.
so then we'd say,
Behind again.
P of N. Oh, actually, we should have written that as the third, yeah. That was
After
down.
you've proven a base case, try writing out what P of N plus 1 says in your ignore area. And see where you're heading
So
towards.
that would just be 2 to the N, right? If we add 1 to that. Or we have N up here. Or we have 1.
Right.
And that would equal this. We add N. So these two.
All,
I'm just not sure to do this, so I had one of that, all that from that. I need to look at my notes.
So you're basically,
I'm just
anywhere you see an N, you're actually getting N plus 1.
Okay, so
So you got the left side correct.
So we can just do the end, kind of distribute that, so we get 2 actually minus 2 plus
N plus 1, yeah.
then we add this now, so we get 2 and plus 2 and so now I have this giant expression here, so.
Why couldn't you just write it like this though?
So the issue is.
I could, but, I mean,
Or you're just kind of proving yourself?
That's
kind of
that,
proving
yeah.
that, so yeah, these cancel out,
Yours are nice, but you could try to.
Okay, I don't understand, yeah.
which one?
Rewrite that, so and to the two,
I mean, we need dot, dot, dot.
Yeah, plus the dot, dot, dot.
Oh, yeah,
So let me put the last term you got there.
Two, yeah, and then we can just do add these two
Plus,
together,
and then
so
let me
that's
put your new term on
plus
there.
one, plus one, okay.
Oh, that's what we were missing. Yeah, 'cause you still want that.
And you're doing that because if you're assuming P of n, you can replace this.
Okay. Well, wanna move to the next one?
Oh, we can do that. I think we should actually get.
Usually a good way to use.
That's right.
I mean, it is right, but.
And so you're gonna have
It did say
this
something about like,
plus that extra stuff, and now you have to work to show that that's equal
We can
to
just
this.
carve out some space then.
Yeah.
To show that, then you can step backwards and show that P of n plus one is true.
Let's just replace those. Is two times
And I'll do big RCs.
plus that.
Okay.
So we're done with the plus one?
Now it should just be.
Cool, good, good.
So I just did 2n plus 1 here, it's gonna skip a step.
Oh,
2n plus 1 is greater than n plus 1, like that. So I'm just writing that.
So where did this one come from?
If you expand this, probably some of these something. I think we should but I don't think you need to do.
So people are on a good start here. Let me give you an idea where you're going here. So first of all, make sure that you're saying P of n is a proposition. Let P of n be the proposition, which says, and then say what the proposition is. So 1 times 2 to the 0 plus 2 times 2 to the 1, all the way up through n times 2 to the n minus 1 equals n minus 1, 2 to the n plus 1. That's the proposition. And try to avoid saying P of n equals this equals that. Because P of n is not this equation. P of n is not that equation. P of n is the proposition that this expression is equal to that expression. And if you start writing let P of n equal this, it leads to technical errors that end up becoming more than just sort of style errors. It can actually lead you to writing things that aren't true. So let P of n be the proposition, and I think everybody's got a base case down, right? Plug in n equals 1, for example, and this is true. So now you're proving P of n implies P of n plus 1, right? And so people are starting off with P of n, that's a hypothesis, and then write down what that says. Right, so far so good. So this is where I would suggest, see where you're trying to go. Make an area, label it so that someone doesn't take it as part of the proof, and just write out what P of n plus 1 says. And this one's harder than some, because we're basically replacing this n with n plus 1 at the end. So 1 times 2 to the 0 plus 2 times 2 to the 1 plus, and I'm going to write out that last term plus the next term, n plus 1, 2 to the n. And we want to show that's equal to, well, instead of n, it's going to be n plus 1, so this will just be n times 2 to the n plus 1 plus 1. It's not part of the proof, but that's what you want to show. And this is something we already know. This part over here That's that part. And since we know this is equal to that, we can take that and replace it with that. And now we've just got two things added together, and you have to show that it's equal to that. So that's where you're trying to go, and then you don't use that, right? You take this, and you write down what you get when you add something to both sides, and you simplify from there. So keep going from there. Unless you already finished.
Okay, yeah, that makes sense.
So basically, this was, we're adding adding 2 and 2, multiplying this by 2. So what we have to prove is that multiplying by 2 is more effective than just adding.
Sure, yeah.
So which becomes true as
Yeah, like you said, it's down.
yeah, like a more
Right
mathematical
away.
method.
I see, I see. Does anyone care that calculator? Because we need to prove this, so I gotta prove this from the calculator.
We won't need a calculator, will we?
I mean, we could prove this somehow.
To do 4?
I mean, 4.
2 to the 4th power?
16, yeah, so.
So we're going to simplify like this.
So I would say we go, I would say we do,
Wait, 16 is greater than,
So.
yeah, 16 is, yeah, we're saying 16 is greater than,
It's not true for.
yeah, it's not true. Wait, why would we not do?
so it looks really.
I don't know, it's not true for,
Yeah.
So I was like, true.
Yeah, so that's not true.
16 is not greater than
Yeah.
20. But, 32 is greater
Yeah.
than 30. 32 is greater than 30. Yeah, base case is 32 is greater than 30.
So are we going to prove it like by just having the number?
Yeah, so when you plug this in and separate out, I got basically the same thing as the last time with these two changes, right? So basically we have to prove that multiplying something by 2 is going to yield a larger increase
But
than
that
this.
looks like our algebra was wrong.
So the way to do that,
Oh no.
What did you do right here? Oh,
so
we did
intuitively
it.
we understand why this is going to grow faster than this.
That's what I was hoping, okay.
I just simplified the math.
So that's
This times 2
And so this would be n squared plus 2n plus 1 plus n plus 1 n squared plus n plus 2. And I want to get the original thing so we can compare. So basically we just have to say if this side's bigger than this side, we're just taking that as a fact. Multiplying this side by 2 yields a larger increase than just adding 2n plus 2. Yeah, so like now we need to prove it more mathy.
Is this right here?
So we already have a basic case for like 5 and become
Oh, okay. So for this to yield a bigger increase than this, that means that 2n plus 2 has to be always less than yeah, not not 2, but basically for this to be true, adding 2 plus n must be smaller than multiplying what we already have, which is 2 to the n times 2.
I'm thinking of like how we can factor to our calculus, then we have like 2 times n
Cancel the difference.
So we know if you like ignore those terms, we know that's true, that's the given part. So we just have to
Now we
prove
just
that
have
this stays bigger.
minus
Right, this is already bigger than zero.
Cancel out.
Are we doing more?
We're on the edge of understanding the math. plus 2. We're taking some number, and that number is 2 to the
That
n.
was just a start. Like, I didn't change it for how that says freaking. Oh, yeah.
We're saying it's less than. It's less, yeah, it's doubled, which would be 2 to the n. Yes, in fact, he is right, because we're adding 2n plus 2, and if 2n plus 2 is smaller than multiplying this by 2, we're fine, right? And what we're saying is, just say you had 10 here, and you multiply by 2, you're saying that let's just throw real numbers. So we just used our, just like to put numbers on it. Like, so 2 to the 4 times 2. 2 to the 5. We're saying 2 to the 5 times 2 is greater than squared. We know this is true. And we're just going to add 2 times 5. And so if 2 times 5 plus 2 is always less than 2 to the 5, because we're just doubling 2 to the 5. Right, so by doubling it, we could also write this as 2 to the 5 plus 2 to the 5. Right? Is greater than, now I'm going to switch back to 2 to the n plus 2 to the n. Is greater than squared plus 2n. So, we know this is true. So is 2n greater than 2n plus 2? That's basically how is it relative? It's not generally proven. But that's, I feel like we're close. Intuitively, this is so right. Intuitively, we know that 2n is going to be bigger than 2n plus 2.
But
We know this is going to run away, and this is not. Like, we know that's true.
because like this side and that one is only
Like 2 to 100 is way bigger than 202. Right? Intuitively, that makes so much sense.
It almost seems like a hypothesis.
The problem is, we like need mathematical induction.
You're right. I mean, if it was, since it doesn't work for it, it wasn't work. Or is it
We proved the base case of 5.
so it's not going to work for
Yeah, and then we just have to prove that assuming this is true, we need to say that the n plus 1 is true. And I thought by splitting them into the original with basically the changes, we make it easier. Oh, wait, I think I see it. Yes, so if n squared plus 2n is less than 2n plus 2.
I was going to say right now learning this one is bigger
Yeah.
and this one is already n to the power of 2. But what we are trying to prove is 2 to the n plus 2.
Because in a way, this is
Since the given equation already told us, even though the n to the like n
Yeah,
to
we
the
can
power
like
of
use the
2.
definition again.
Yeah. So which means that one's already like smaller than that. Which is true, but how can we put everything?
Yeah, because if we had like this, that would work, but it's that.
It's still smaller
We
than
don't
that.
actually know this is true. I mean, it is.
You gotta clap twice.
But I think, yeah, so maybe I'll just draw it here. So for the n plus 1, we basically have 2 to the n plus 2 to the n.
Yeah, that's
We're doubling
not
it.
just right down
It's the same thing as 2 to the n plus 1.
That's one, yeah.
So 2 to the n plus 1 equals 2
And
to
then
the
right
n.
now, see.
It's like, we wouldn't write it as a proof, we would just be saying that that's greater than where I'm n plus 1. So I'm just going to factor it all out where I was before. N squared plus n
Okay, so.
equals 2.
So we want to go like, and
We know this part's true.
Yeah. So all we have to do is prove that 2n is still bigger than 2n plus 2.
Yeah, if we know this is bigger than this, then we're good.
Can we prove that,
It'd be better to get some, like, if we get like this form or something.
can we prove that this one is smaller than this?
There's the one going into.
Yeah, if we can prove that, then we can prove that. I was thinking that, but technically, no. I mean, for example, n equals 1. We could prove that with mathematical induction, and then we could prove this with mathematical induction. But
Feels like double.
then we have to use it again.
So that is simple.
The n squared plus 2. I mean, we could try it. That'd be a way to do it in a really creative way. Let's do it.
Now it's just.
So now we're going to prove using mathematical induction again. Let's say that let's p of n
Yes, so, well, so,
be
What
the
did you say
problem
that was?
minus 1 is just gonna be n, so
that
this whole thing is
n squared plus n is greater than 2n plus 2
Is that what you were trying
So this should be easier, right? Intuitively. That would be base case. Base case is easier.
Because like,
That's 30. So base case would be 30 is greater than 15. That's true.
if we're starting with like n to. You make your own
version.
But then when you score one of them, it's double and like, this one is gonna be bigger.
Really?
Not for n equals 1.
When
Right?
n is
Because,
bigger than two.
yeah.
But with
It
our
has to sort of be
equation,
generally.
but still for our equation is like n bigger than 4.
Yeah, I know. I'm trying to think if like we're allowed to do that because I feel like I feel what you're saying. It makes sense. It's intuitively true, but is that formally provable? I mean, this would be really easy though. Basically, we're saying we know that. We'll just give the depth. And say
P of one.
that's true. The hypothesis. So we're gonna
Also, you're doing like two
yeah,
mathematical.
just doing it again. And then once we have this, then we
Then we
finish.
can prove that one.
It's probably not how you want us to do it. As long as we prove this, this should be easier. So let's just add
And this one.
I'm just gonna factor it out already. It's easier that way. Okay. N squared plus n plus 2n plus 2.
This one and then do another
It's
one.
greater than
Plus 3. Oh, wait. 2n plus 4.
2n seems like we're running the same problem, but infinitely stack overflow mathematical induction.
P of n, right, so you've written that out.
And then like, well, clearly 2n.
That's just.
Isn't that 2?
Oh wait.
That was kind of.
Actually, we got it.
So
Right, 'cause this
essentially
is
we did
2n
the
plus
same
2
thing.
plus 2.
Right here.
This is
We
n
just didn't
squared
look at
plus
this left side and just
Plus 2n plus 4.
around this whole simplified it.
Wait, is that
Kind of
2?
doing cancellation. It actually works better for us because then it got
That
us.
one cancel out. Obviously, everything is bigger than 2. So because like,
Because otherwise we need the acidity.
Yes, yes, so that cancels. That cancels. So then we're saying n squared plus n is greater than 2n plus 2 is greater than 2.
All right, so let me talk about this one a little bit, and then we'll go on to another one. And if you want to figure this one out on your own, keep working on it. But I think people have the right idea here, right? Basically, we know this, right? That's the definition of the hypothesis, that sum on the left is equal to the expression on the right. What we want to do is show that this slightly bigger sum is equal to this other expression. So we can start with this proposition 2, right, and do whatever we want as long as we do things that are legal, like adding the same thing to both sides, or simplifying expressions and so on. And for this type of problem, right, this expression on the left that we already know something about almost looks like this expression on the left, right? In fact, if we take this expression on the left of proposition 2 and we add one thing to it, n plus 1 times 2 to the n, we've got the left side of p of n plus 1. So an idea is rewrite this right. That's still just proposition P of n, but let's add something to both sides. Let's add n plus 1 times 2 to the n. I've added it to both sides. This is still absolutely equal. But now, my left-hand side over here looks like the left-hand side of Pn plus 1. Right, that's why I added n plus 1 times 2 to the n, because I knew it would make this look like that. If I can show that this right-hand side looks like that right-hand side, I've just proven P of n plus 1 and I'm done. So now the question is, can we take this and somehow by doing just algebra and other legal things make it look like that right-hand side? And so that's the level of sort of the algebra trick part of it, right? Where you mostly, combine terms, get rid of parentheses, try to put things together and then see if you can somehow factor something out. It'd be nice to factor out a 2 to the n plus 1 or an n, right? And so that's playing around with it. The critical part is basically, stating the proposition, stating the base case, showing the base case is true, stating P of n what it is, and then there's this bridge to cross where you turn this into something else that eventually lets you say P of n, or sorry, P of n plus 1, and then you're done. So I'll leave that one for now. If you didn't finish it, right, think about how you can turn this into, right, and ask me later on if you don't see it. So let's try an inequality. No, I don't want to do an inequality. Let's try one like what you just did. Let's do number 7.
On the board?
So prove that, yeah, on the board. So prove that the sum of the first n squares is equal to n times n plus 1 times 2n plus 1 over 6. This is like algebra workout day.
Because once we used a recursive mathematical induction for this.
Oh, let's see.
For the second one.
Oh, okay.
Because we got to here basically, and we thought intuitively like this is bigger than this. We did not approve that, but we thought that we could prove that. We know that this is bigger. This is smaller than this.
Okay.
So we thought, okay, we can prove that this is smaller than this.
Okay.
Then we did. So then we did a mathematical induction for that.
Okay.
Yes.
Cool.
And then we proved
Cool.
that that worked.
Oh, nice.
It's probably a better way to do it. But
No, that's good. I like it.
I don't know, like maybe would have been fine to just. I felt too like loosey goosey to kind of
So which one
just
was
say because
this?
like intuitively we understood this one. Yeah. So like when I was, this is like the ignore section, but intuitively I just added.
You notice it's like purple or something?
Assume P of n, so assume 2 to the n is bigger than n squared plus n.
This is
So
the
you want to
string.
show
Want to do this or should I?
2 to the n plus 1 is bigger than
Let's
n
go with it.
squared.
Yeah, just up there.
It's like this first step. Even
You have that. Okay, good, good.
All of that.
So we added 2 to the n to both sides.
Mm-hmm.
That wasn't what we did though. So what we did was we we just wrote n+1, which wouldn't have been valid for proof, like over in the ignore section. We expanded it, and we got to here, and so we knew like, okay, well we know that that's true,
Right.
so we just have to prove that, and that is the same thing as adding 2 to the n. So only if we can prove 2 to the n is bigger than 2 to the n plus
Right,
2,
right. Yeah,
then we can
yeah.
prove that.
That's the way to do it.
Obvious is 1, right?
Right, so you know that's true.
Yes.
Right. Which is 2 times n squared plus 2. And then, so you show that's bigger than that.
Yeah, so we need to get like a 2 to the n plus 2 out of it somehow,
Right.
which is why we just did mathematical.
Show n squared plus 2n is bigger than 3n plus 2. Show n squared is bigger than n plus 2.
So would it have been fine to say, well, we know that all these n's are going to be bigger than 4? Would that have been
Right.
invalid?
No, that's why.
Oh, that would have been
you know,
okay.
n's bigger than or equal to
Okay.
5. Yeah.
So that would have been, because the only my only thought was, are we supposed to ignore the fact that the base case had a real number?
Nope. No, you
Okay,
have
so
to
we're
use that.
so we're allowed. Okay.
Yeah.
That would have made things a lot easier.
Yeah. Otherwise, like if you put in a 0, I don't know if it's true.
No, it would never inequalize or never true. Yeah. 0 through and everything. Yeah, multiply both sides by 0. You got it.
Yeah, yeah.
Okay. So we would have been fine to say something like,
Since n is at least
since
5.
n is bigger than 5,
Right.
this is true.
Yeah,
Okay.
yeah.
Oh, that would make it easier.
So we don't have to go
You don't have
through
to
it.
recursively.
Yeah. I was going to do this one on the board next, and that's why I changed my mind, because
Okay, so now we can do this next one. Let given proposition up to n squared equals that thing.
On this side, what would be?
There's a n plus 1. That's easy.
And there's a.
There's a so just like because we're in our section again.
We're just adding more ways, clause to the side, change everything.
We don't actually have to put that in our proof, but yeah, that's fine. Yeah. So we just
I mean, that just has to be.
one is equal to that's gonna be 6. Right, this is 3, that's 2, that's 1. Wait. Yeah.
N plus 1 times n plus 2 times 2 times n plus 1 over 6. I can turn each of those into n and n plus 1.
That's what we do in the first one, not multiply. But the way he did it on the screen.
So that's true.
We just add on some numbers, I guess.
Is this it? That one is it, right?
Just add n plus 1. N squared 1. Yeah, that works.
Oh.
But we have to prove that whole thing.
So we can't write that in the proof. We don't know that. That's what we're trying to prove. That would be the yeah.
Yeah, that's right. He probably simplifies it. Yeah, he's right. So instead of like we wouldn't ever want to minus that, you know, we want to simplify this into looking like
So over there.
like what I said earlier about n plus 1 times n plus 1 plus 1. You know,
wonder if expanding that would do us any
I
good.
think that's.
Exactly, that's what I figured too.
That's a good point, so I guess we do do it on both sides. So.
Yeah, we could just expand it.
Yeah, expand everything.
And so that'd be n squared plus n times 2n plus 1.
So,
N squared plus
Maybe
one
n
times
first time around, we basically
Yeah. All right, I'll do it one step. So n squared plus n times 2n plus 1. That'd be 2n cubed.
we just replaced
Plus,
right?
No, plus n.
yeah, plus n squared
Yeah, that's
plus
what-
2n
But
squared.
what I'm saying is
plus
now
N.
is the exact same.
So yeah, we would do 2n cubed plus 3n squared.
I think
Or 6.
We got it. Okay, let me think. Well, I think last time we didn't have that on the other side, so I think.
Yeah.
Oh, that's 14.
Plus n plus 1.
Last time we did it, the way you're talking about, where we, for everything.
Yeah.
It doesn't seem like.
I think that's now what we're trying to get one side to like. I don't know.
We just try and do that?
I think we might be doing it as well.
Which means that this is a direct primary.
Oh yeah, okay, so we need to basically like dive this back into here somehow, and then we need to come out with basically the n plus 1 version of that, and then we know we can. Okay. So just be on algebra. So we could.
I think that was
Weird.
in
So I think that would just be
I think that
because like we're adding.
we're trying to get, I think now we ignore this side, because we know that this equals that, right? Equals this right here.
Okay.
So now we
Yes,
just
yeah,
want to
exactly.
prove that.
Yeah. So that's we just need
Now we
some kind
want
of
to prove
algebra way
that,
to
no,
do that.
we have to use that.
There's actually a way. Obviously, like getting rid of.
Well, let's try that way where it was like n plus 1.
Yeah, we can keep that. The thing is, we gotta fold this in here somehow. So we could, what we could do
Yeah, I
is
think that's what we're
write
trying to prove.
6 times
That's
this.
what-
Okay, you're gonna write 6 times this.
And it's
Yeah.
one. Otherwise,
And then we can
Let's
add that
actually
in.
write that down just for now, let's not assume that that's right, just to write that down.
I know, because we're gonna put it all under 6.
You don't wanna like assume.
So I'm basically folding this into here, so I just had to multiply by 6 to fold it in.
Yeah,
Get
and now we just want to get this
I have a
side,
feeling this is
flip
gonna
this
work.
side, right?
But, so if we, I have a feeling that's kind of what it's going to be. So n plus 1 squared is n squared plus 2n plus 1.
Yeah, so now it's kind of like that. Like right away, we can figure out
Yeah.
the n plus one.
So 2n cubed plus n squared plus 2n squared plus n. We got that n there, right?
Yeah.
And now let's add
What would that be? 2 times
6n squared. And this is 6, and then all that over 6. I think this will work. Looks like it's factor. Someone can do it.
6, 8, 9, so we have,
You just need to factor this whole
yeah, 2 cubed plus 9 squared. And then plus,
Yeah, it works. Yeah.
but I mean, you have to like write a stamp.
Yeah. This is the other n plus 1. So you have to show that all of them are 1. Yeah, so it
Like
actually
a
works.
floor section.
Maybe this one.
Yes.
What?
Yes! Yeah, we're gonna write this whole line.
That was awesome.
As long as you write true statements, it works. So
That
if we
probably
write
makes
that,
that smart.
we can write, oh yeah, so we could write the n plus 1 square on each side. So that's basically right. Yeah.
That problem made me feel smart.
Excellent, did it work out?
I think so.
Yeah, so I was actually wrong. You wrote that correctly.
What
So
happened?
we weren't assuming
Boil
this.
that out.
We just added. Yeah, see, that was actually mine.
Yeah.
My bad.
The only thing that I was scared about is
Yeah, so that is great. And then from there we get algebra, C appendix. Yeah, when we then approve, so that, yeah, then we approve PM, yeah, P of n plus 1. Therefore, P of n. I don't know where that extra n came from. That took us back to.
okay, so.
Yeah, that looks good.
Rewrote
That's really
this.
good.
I'm trying to get it to look like that. So we have that n plus one, now we need to get this into n plus two, and then to n plus three.
You feel smart?
No.
Not yet. No. Look, we got some.
Okay.
Two of them.
No, you're doing great. So P of n, right? And you're trying to
Oh,
show.
sigma? Like a summation or something?
So, yeah, it's an algebra exercise, so yeah, we'll figure that out. That's good.
Okay, we can do it. Oh yeah, we can do 8. Prove that n squared minus 1 is dissolved by 8.
Yes, yes, it does.
So I think if we get this to look like.
We probably shouldn't use the module if I make it messier. It's going to ask me to play whenever n's. Oh, this is interesting. So now we're n squared minus 1. So we can prove it for some case. So let's just prove it for when n equals 2.
One thing that, yeah, we're gonna work on.
Oh, awesome.
So n equal 1. I mean, it's still like.
Yeah, proved it.
What about two?
Those are
9.
odd numbers.
I mean, it'd be a 3.
Yeah, that works. That would be 8.
5, 24. Yeah, that was 4. So like, is that whole room?
All right, so let me talk about this one. I'm gonna bring the shade down for this. All right, so what's going on here? It's a similar setup to a lot of the other ones we've seen. So prove 1 squared plus 2 squared plus n squared equals n times n plus 1 times 2n plus 1 over 6, where n is bigger than or equal to 1. Right? Start with a proposition. Okay, that's what P of n is. So P of 1 says the sum of the first 1 squared is equal to 1 times 2 times 2 plus 1 is 3 divided by 6. That's true. So you have a base case. Proof P of n implies P of n plus 1. So step 1, P of n, that's your hypothesis. Step 2, write out P of n. And it's important to write it out because it's going to help you see what to do. And don't be too conservative with how many terms you write out. Right, I'm going up to the n squared. I might have wanted to go up to the n minus 1 squared because you're looking for patterns, right? But this is what P of n says. Okay, so now I'm going to say ignore. I'm going to say I want to show this holds if I plug in n plus 1 in place of n. So I want to show if I do 1 squared plus 2 squared plus n squared plus n plus 1 squared, that I should end up with n plus 1 times n plus 2 times 2n plus 1 plus 1 divided by 6. If I can show this, I can say P of n plus 1 is true, and therefore Pn implies Pn plus 1, Pn for all n by mathematical induction. So my whole proof comes down to, can I show that this is equal to that? Okay, well, I've shown that this sum is equal to that expression, which means that I can take this part and replace it with this quotient, right? So without ever referring to P of n plus 1, I can say 1 squared plus 2 squared plus dot 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 plus n squared plus n plus 1 squared equals, and I can just plug this in for those first n terms. This is equal to n times n plus 1 times 2n plus 1 over 6 plus n plus 1 squared. And now all I have to do is show that this is equal to that. That's algebra. And it's kind of yucky algebra. It's got cubics in it if you just multiply everything out. But you can get there, right? The biggest issue is making mistakes in the algebra, because then you can't show they're equal because they're not. But you know, you can just completely multiply this out. You get some n cubes in there. Multiply this by 6 so you have a common denominator, add them together, and then turn that into this. Okay? And this is worse algebra than you would typically be asked to do on a test. But let me tell you what you do not want to do. Okay? Here's where this becomes a non-proof. So I want to prove that this equals n plus 1, n plus 2, 2 times n plus 1 divided by 6. This is a sub-problem. If I can prove this, then I can prove that Pn implies Pn plus 1. Okay, here's what you might do that will get you into trouble. So here's a comment. I'm going to multiply both sides by 6, so I'm going to say n times n plus 1 times 2n plus 1 plus 6 times n plus 1 squared equals n plus 1, n plus 2, 2 times n plus 1 plus 1. And now I'm going to divide both sides by n plus 1. I'm going to say n times 2n plus 1 plus 6 times n plus 1 squared equals n plus 2 times 2n plus 1 plus 1, and so on, and eventually I'm going to come up with something like, you know, n equals n. Okay? That is not a valid proof. Okay? Because this is not a proposition that I know to be true. This is what I want to show. I want to show that this side equals that side. If that's true, then this is also true. And if this is true, then this line is true. And if I keep doing that and I eventually show that n equals n, I've proven that n equals n if this is true. But I haven't proven this. Your goal is to prove this statement. If I write that down and I start making changes, I am proving other things that follow from this. But that doesn't prove this. I'm trying to prove P, and so I write down P and I do some other things and I come up with Q, and I know that Q is true. Does that mean that P is true? Right? I can start off with saying, you know, I am rich and famous, and I can do some other things and I can prove something that's true, like I eat breakfast every day. That doesn't mean I'm rich and famous. That just means if I'm rich and famous, I eat breakfast every day. Right? And the sillier example of this is, you know, prove n equals n plus 1. Well, I can say n equals n plus 1, and 2n equals 2 times n plus 1 equals 2n plus 2, and 0 times 2n equals 0 times 2n plus 2, and 0 equals 0 times 2n plus 0 times 2, 0 equals 0. That's true. I just proved n equals n plus 1. It's not a proof. right? If n equals n plus 1, I've shown 0 equals 0, right? But that does not prove, right? That's the converse, trying to say that since this is true, that's also true. And we know the converse doesn't always follow from the original. So when you're doing this kind of proof, right, we're trying to show that this is equal to that. Well, you can do things to this. I can expand this. I can multiply by 6 and put it over a common denominator. I can multiply this out and get the cubics. I can combine terms, and I can try to factor it into exactly this. And once I've shown that this is equal to that, then I say that's what p of n plus 1 says. And then you're done, except for, you know, dotting the i's. All right, so that's something to keep in mind. All right, let me change this up. Let's totally switch gears. Let's do a problem that doesn't have any extreme algebra. It's got some algebra.
It's either extreme or not.
Yeah. So let's do number 9. So suppose that there are n people in a room, n is bigger than or equal to 1. Let's say n is bigger than 2. And they all shake hands with each other. Prove that n times n minus 1 over 2 handshakes will have occurred using mathematical induction. So P of n is the proposition that if there are n people in a room and they all shake hands with each other, that n times n minus 1 over 2 handshakes take place. So try to come up with an inductive proof of this. In other words, write out P of n plus 1 in an ignore section, and think about how you get from P of n to P of n plus 1. What happens when one more person comes in the room and everybody shakes hands? How is that related to the case when there's n people in the room? So play around with that for 15 minutes. Or until you get an answer. And let's see where it leads.
N times n minus 1. Maybe. I mean, you just prove the base case and then. Yeah, but.
I don't know.
No, 6.
Yeah, because like, I'm thinking about how many people and how many handshakes.
It makes sense intuitively, right? Because if you have 4 people, then everyone shakes hands with everyone, except the person can't shake their own hand. And then half of the handshakes were between the same people. So it's essentially
She was saying like using that word.
yeah, I don't know. We can prove the base case by using, we can just start the proof. So
It doesn't work for one. For n equals
it works for one. If you're alone and you shake someone's hand, how many people's hands did you shake?
Well,
They're out.
yeah, it makes sense.
So it actually does work for one.
Basically one.
Yeah. Maybe someone can write the proof.
What did you say?
Yeah, when you only have one person, you shake.
Then if
You can shake 1 time. No, 0 time.
Yeah.
When you have 2 people, it's 1 time.
So basically, knowing this,
Yeah,
Then
we see lines
and
like
then
So if we add,
Oh, yeah, that's number. You can't do math.
it's just something to look at it.
So, since we're assuming
yeah, so this is what we get, if we add n plus one, we get this.
If one person shakes another business owner,
Counts
is that
two
one?
handshakes.
Because when we're trying to, like, mathematically, what we wanna end up getting, we wanna end up getting
Is that a different?
that.
No, so if two people shake hands, that's one handshake.
You don't really have another side of
It
it.
doesn't matter who started it, yeah.
Five, or 6, 15.
is this we're trying to prove?
Plug it in.
Yeah. So you can think about this in terms, what happens if a new person comes into the room? How many- how does that
Well,
change
not
those
equal,
people?
But it's not like.
Yeah.
You could, just write it down.
Whatever, this one.
Right. That would actually probably be
I guess like PO labels, PO.
Yeah, handshakes.
Add one to one, it's number, and add it.
Right, it's a parabola. so-
Yeah, it's interesting though, because we need to find a way someone to put it in a mathematical
Yeah.
form that works.
So this, let me just.
Like give people.
And our proposition is, whatever, if everyone has handshakes. Right?
Yeah, how would you?
Weird one. No, that's why we had zero
Yeah,
handshakes.
zero went here.
There's no.
You know, maybe we don't need to even use mathematics. Maybe we could use the stamp. Remember the stamp trick?
Yeah.
He didn't really.
Yeah.
Like a,
Yeah, the intuition for this is not really mathematical heavy.
I think that would be the better way to do it. So, knowing we're gonna do it that way, we don't need. So yeah, we'll probably write the thing. Yeah.
Yeah. So what's the base?
Two people, two minutes, two.
I'm literally trying to decide because that was gonna be
You could actually just
This is brain free.
basically connect the dots to the graph. So if you connect the dots to a graph, it's like getting a graph theory of your dude. And these guys.
So it looks like the numbers, the numbers of handshakes equals the number of people. Because there's
The matrix doesn't. Remember, one guy gets zero.
You don't shake hands with yourself.
Right, because one dot, there's nothing to connect it to. And we need to connect these.
Yeah.
These to connect. These to connect. These to connect.
So do you want a hint how to think about this?
No.
I'm hearing snippets of it from some groups. So let's pick an example. So there's 5 people over here in the corner, right? And they're in a room. How many ways can they shake hands? We're assuming it's given by that formula. Okay, so those 5 people can shake hands 5 times 4 over 2, 10 ways. Okay, we're assuming this is true for 5. We want to know, if we know the formula for 5, how many ways can people shake hands if there's 6 people? Okay, so if one person comes over and joins this group, and now everybody tries to shake hands, you have all the handshakes that would have taken place with just the 5 of them, right? And you also have all the handshakes that will take place that include the new person. That's the total number of handshakes. Well, the number of handshakes with just the 5 of them, that's 5 times 4 divided by 2. if there's 5 people in the room and a new person walks in, how many ways can that new person shake hands? 5, right? Because they can shake with each person who's already in the room. So when you add a new person to a room that has n people, the total number of handshakes goes up by n. Okay, that's the formula you can use to connect this formula for n people to the number of handshakes when a new person enters the room. It's going to be this formula plus n. If you know that, then you can try to show that that supports p of n plus 1 too. In other words, that's the same formula you get for p of n plus 1. So we have 5 minutes to play with that.
So that's what we have. This is true. And we add something. So then this would be the n plus 1 case. Well, we factor these out, right? This equals that, this equals this. N squared minus 2, minus n over 2, n squared plus 2.
Okay.
We want to compare this. So basically saying, how many more handshakes happen? Well, n more handshakes happen, right? Because if you take n squared plus n over 2 minus n squared minus n over 2.
Oh, you're right.
What are you going to get? Well, we can multiply by 2, and then we get n squared plus n minus n squared plus n all over 2, so we get 2 handshakes.
This makes sense logically, is where like adding what one or something. Mathematically,
We know that this formula works for n.
Oh, yeah.
Another person.
like mathematically, because since this is minus 1, it will work plus 1.
Oh, I forgot a really important piece. I see. Wait, no, I was thinking about
Like,
All the new
for that, like,
handshakes.
like adding one, so basically like different.
Yeah, I flipped them, but I didn't. I flipped them back there.
So if this is the number of handshakes.
So the difference of people should always be
Say absolutely this is the
Always.
number of handshakes.
and intuitively we know the difference should always be n. And in this, mathematically, the difference is always n.
And then you do the all.
Somehow we have to
Like this.
show that,
So,
and that's why thirty-eight
just take out the left side of the image or, and then we'll write the definition. So we'll say something like n times n minus 1 over 2 plus a first.
So that's the thing of doing the formula. Right, they can shake hands. Now a new person goes in.
Yeah, I want to make sure we shake hands. Plus a first, all the handshakes go.
And you got all the handshakes.
Okay, so let's say.
Can we say that this one minus
Yes.
So 5 people, one just walks in, they say,
I could say,
Right, so we could say,
And then
that's why it is like 0.
then you're just showing that this is equal to that.
say that this equals, this
Observe this is the
equals n.
right, and so once you
Maybe not even do this manually, I don't think I would make the should say. That's our, the definition
So
is
this is part of your,
something like,
this is part of your.
That's the answer, not the explanation. That's the right side.
Yeah.
What's the left side?
So how many more handshakes occurred?
One, because you
What was
don't
it?
represent
Was it N more occurred? Yeah, right, because this one's
it's not
six,
quite
and
hard
this
enough to be
one's
approved,
six,
yes.
right? So we know.
So this is the left side. This is, I don't understand how this is in the group. So for every person.
And what's the number of
know,
people?
so.
Yeah.
you could write just that, it's right out. And times n minus 1 over 2,
it's an expression
n times n plus 1.
I guess I'm having trouble understanding what.
Minus this. This is
The definition was the statement of P of n.
It's going to equal n.
I'm
And
saying.
then some logical reasoning would
Yeah,
show
the left
for
side.
Reduce or
It's
less
always
than.
something like this.
Right. The original group of n people will shake hands in both ways, and then
People handshake in a room. This is not real.
that,
And then
that.
people don't.
And then I look at what P of n says, and I say, well, this is P of n.
right here though, we're using that.
Oh, I'm just doing the algebra.
Oh, you're doing the outline.
Yeah, so I'm sure let's do that now.
So if there's n people, then
But then you're doing the
and if you're adding one more people,
Okay, well, I was thinking about that.
Yeah, doing it.
it's already like one.
Oh, and that's kind of just like, just use this.
Yeah, yeah.
Okay, let's.
Yeah, I understand what you're saying.
Huh.
Just making sure it's like
So
formal
does
enough.
this represent like the total number of people?
Does
Or
it need to be this?
Because
Taylor, like this,
these two or this person.
Price of students and grand total.
This is handshakes. So we add in plus one people, we get 10 more handshakes.
So why is not this thing?
Yeah, it's not the name can get confusing, but this is handshakes. This you got all in right this way, I guess.
Just plus one.
People, just people.
Oh, so that
and,
is.
extra events.
Okay.
I said this minus this equals this.
I'm just gonna.
This shouldn't really be in the group, but it's just helping us keep track, right? We're saying the difference in handshakes is when you add one person is it's the amount of people. Yeah. But it's not really clear.
And then it says like prove that handshake
Number of ways that one people shake hands.
Yeah.
So we can say something like this.
Number of ways that
You add a person.
You're adding, the
Then-
denominator
you
stays.
got steps right. You got the algebra right.
I'm gonna shake everyone's hand.
The last piece is just sort of how that is explained.
That's the next one.
So that it's
Here we go.
clear that number of handshakes will be shaken by.
Everyone
The only
was.
thing that's missing is saying this is the number of handshakes.
If you had a person, then you would shake everyone's.
Explaining like this is the number of
Oh.
handshakes.
Yes.
Yeah, I don't know. I just.
There are n people.
So right there,
Say therefore, if you had plus one.
I didn't actually put in, I didn't plug in.
There are.
Yeah, so right here, I actually added on the end, and then I simplified it down. Which I don't know.
One.
Either way, you end up in the same thing, so.
Yeah, go ahead.
Okay, so did you catch what I mentioned?
Never, someone walks in the room, and we're already shaking each other's hands.
Yeah.
We also gotta shake each other.
Right, so we
So you say all of us are shaking hands, and someone new comes in, so you gotta shake this one's hand. I'm just gonna shake 10 people.
The number of handshakes plus N.
Say again?
N plus one is another rule, we would just. Number of handshakes will be increased by.
Oh, yeah, I can try to counteract here, the next iteration. Subtract it from, basically, this, we could say like, this is the difference.
Oh, yeah.
Basically, more handshakes.